Our last speaker of the day is Subramanya Hegde, and he'll tell us about on-shell functions on the Coulomb branch of n equals 4 super Young-Mills.
Hi everyone. Thank you for staying so late. It's been a very exciting day and a very smooth workshop. So I'll be speaking about on-shell functions, which Shruti introduced very nicely to all of you. In particular, its extension to what is called as the Coulomb branch of n equal to 4 super Young-Mills. So now I am at MPP. When I did this work, I was at Institute of Mathematical Sciences in Chennai, and these are the people I work with. So let me start with some motivation. As all of you saw in most of the lectures in this workshop, most of the developments in on-shell methods have been for massless particles, and amplitudes of n equal to 4 super Young-Mills serve as the prototype or the simplest amplitudes in the sense of on-shell techniques. Now, one obviously has to extend it to massive theories because we have in nature spontaneously symmetry broken massive particles. And the spinor-Helicity formalism, which was quite crucial for many of the on-shell techniques, was developed for massive particles in a little group covariant formalism relatively recently by these people. And its extension to on-shell supersymmetry was done by Hegde, Coulomb, and Trott in 2019. And in a parallel work, they also developed a formalism to compute n equal to 4 super Young-Mills amplitudes when you have an internal spontaneous symmetry breaking. There are scalars in n equal to 4 super Young-Mills. You can give vacuum expectation value to these scalars and induce spontaneous symmetry breaking, let's say from a gauge group where you have U sum over I and I to product over I U of Ni. And in this general setup, they showed that under the massive supersymmetric BCFW shift, the tree amplitudes are recursable. There is no pole at infinity. And there are earlier results using what is called as the old massive spinor-Helicity formalism that for n equal to 4 super Young-Mills Coulomb branch amplitudes, the triangle master integrals don't contribute. And using dual conformal invariance long ago, coefficients of box diagrams were computed in a simpler spontaneous symmetry breaking setup. So then the question is, using modern on-shell methods, using little group covariant spinor-Helicity formalism, can we compute coefficients for these coefficients for the loop amplitudes in this theory, and also understand the structure of BCFW recursability of this theory. And as you heard from Shruti, for massless n equal to 4 super Young-Mills, there exists an on-shell function formulation, which manifests the fact that loop integrands are D-log forms, and it encodes the BCFW recursability of the amplitude. And you heard how it is obtained by gluing 3-point amplitudes, and all the internal legs are on-shell now. And you integrate over the Lorentz invariant phase space of each internal leg. And this naturally gives rise to BCFW recursability of the amplitudes by a construction known as the BCFW bridge. And we will perform this construction for the Coulomb branch. So this is the brief technical introduction. So where this is just the massive spinor-Helicity variables, you have a maximal rank matrix, which you decompose into spinors. And for the supersymmetric version, where you have the Coulomb branch amplitude, even though it's a massive multiplet, it has the same number of degrees of freedom as the massless super Young-Mills because the spontaneous symmetry breaking is internal to the multiplet. So you just have to rearrange the fields of super Young-Mills in an on-shell superfield, which manifests only an SU2 subgroup of the R symmetry, and these A are those indices. Now, Hegde, Coulomb, and Trott, using BCFW, they calculated, for example, the 4-point amplitude. They also calculated the 5-point, and they showed that there is no pole at infinity. So in principle, you can recurse these amplitudes. What is crucial is that for non-zero amplitudes, you need this condition to be satisfied, which is the sum over masses with some signs must add to 0. And this is what makes these amplitudes quite special. And one more important thing to remark is that in super Young-Mills, the pure Young-Mills also has valid BCFW shifts, whereas in the massive case, there are no valid shifts for the non-supersymmetric massive amplitudes. So the supersymmetric Grassmann variables are crucial. Now, what we did is to construct a BCFW bridge formulation for the BCFW shift by Hegde, and Trott, and we slightly extended it also. And it goes in the following manner. So we have an on-shell function, and we consider a bridge which takes it to a lower on-shell function. And what could happen is that in the spontaneously symmetry broken theory, there are both massive and massless particles. So this A and B could be massive, 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 massless, and so on. So when A is massive and B is massless, and this particle I is massless by mass conservation in this 3-point vertex, then we obtain the BCFW bridge construction for the BCFW shift provided by Ballav and Manna. And when this is massive and this is massive and this is a massless leg, then we obtain the BCFW bridge for the construction by Hegde. But we also have a more general case where this internal leg could also be massive. And the relation goes like this, where you can see that if we set the external masses to 0, then this Jacobian factor disappears, and we go back to the n equal to 4 super Yang-Mills case, where you have the BCFW bridge without any extra factor, but this kinematic factor is there in the Coulomb branch. And the intermediate bridge momenta can be written. This is a particular form which, when you set the mass of the intermediate particle to 0, it goes to Hegde's BCFW, Hegde et al.'s BCFW shift. But we could also introduce auxiliary directions, which makes, in terms of which you could write PI in a sort of a little group covariant way, which lets you pick any of these auxiliary directions. You can do BCFW shift along any of these auxiliary directions. And what we saw was that there are these special kinematic U variables, which Amit discussed in his talk. And in terms of the special kinematics arguments in terms of the U variables, we could argue that the bridge momentum has to be this. And then the analysis of the BCFW bridge here could be repackaged into this. So there is a nice way of combining, just like in the n equal to 4 super Yang-Mills, whereas there is MHV and MHV bar, through which you can argue from the parallelness of square and angle spinors, you can argue the bridge momenta. Similarly, you can argue it in the Coulomb branch. And there is a particular special case, if you want to focus exactly on the Hegde et al. Shift, then the bridge momenta Pi is massless. Then the on-shell conditions, because every leg is on-shell, there are 3 on-shell conditions provided by the bridge. And the bridge on-shell conditions tell you, for example, that the Pi has a vanishing dot product with Pa, which tells you that this square spinor is proportional to this angle spinor. And same on the right side with PB, which gives you 2 conditions. And what we found is that the ratio of XL and XR are fixed in terms of external kinematics, in terms of Mandelstam's, and the other independent combination gives you BCFW deformation of the lower point on-shell function. And similarly, as you saw here, even in the more general case, we have a interpretation in terms of the three particle kinematics variables. And once we have an on-shell function, it lets us calculate maximal cuts of loop amplitudes. So we calculated maximal cut of this single box, which has mass conservation at each vertex. And similarly, we can do higher loops. For example, this is a 2-loop example, where after doing the maximal cut, you see here, these are the shifted SA hats. So in the end, you will see that, and they also have a 1 over Z in them, the shift. So in the end, you will see that there is a quartic polynomial in Z, so dz divided by square root of a quartic polynomial. So generically, these integrals can be elliptic. And we could actually consider configurations where the sum of the masses are 0, which makes everything sort of the square roots disappear. And we could actually integrate the final integral of the maximal cut, and we could do it up to n loops for this ladder, where it's a slightly general configuration more general configuration than what Johannes and others considered some time ago, where here these masses all could be different. The internal legs are massless, but here these masses could be different as long as mass conservation is valid at each vertex. And when you set different masses to 0, it smoothly goes to the super Yang-Mills results. So now that we have done this, what are the future directions? Coulomb branch amplitudes also have dual conformal invariance if you scale mass in a certain way. So this was argued by various people several years ago. And one important thing to do is to use this as a guideline to see how to build higher point tree and loop amplitudes. And another thing which Amit talked about is that now currently we have a symplectic Grassmannian description of the 3-point Coulomb branch amplitude. And the on-shell diagram tells you why 3-point amplitudes are important, because ultimately you are gluing 3-point amplitudes to build higher point amplitudes. And one important thing to do would be to amalgamate these 3-point amplitudes and reproduce the kind of Jacobian factor that we got when we tried to glue 3-point Coulomb branch amplitudes. And in particular, in the symplectic Grassmannian description, so while we have a general argument for structure at endpoints for momentum and supermomentum conservation, it's not clear what are the natural minors that we should put at endpoints. And we think that this kind of gluing of the on-shell functions results that we already have will give us a concrete idea of how to amalgamate these 3-point symplectic Grassmannians and what should be the choice of minors. Yeah, thank you.
Actually, I have two questions.
Yeah.
The first about the failure of the non-supersymmetric case of the BCFW.
Yeah.
Is it something specific to the BCFW shift, or is there some particular contact term that you can write, which you kind of cannot exclude in the recursion? Because typically, if there is such a contact term, then no recursion works, right? Because you cannot fix the amplitude, or if it's some technicality for BCFW. For example, if you use online shifts, would that potentially work?
Yeah, we haven't studied this, but there is a paper by Wu et al. Where they study very general massive BCFW, and they argue that there is no shift that you can do to recurse just massive vector 3-point amplitudes.
And then the other question, so your mass configuration is completely generic.
There needs to be mass conservation. So in that sense, it's a 5-dimensional Coulomb branch setup.
So in each vertex is mass conservation, but other than that, it is
Other than that, it's completely generic, and we have the symplectic Grassmannian in that case, and we also have BCFW bridge in that case. So everything works out.
Okay, thank you.
Any other questions? Have you looked at 4-point? Does it actually do the bridge thing and make a, can you write it as an integral over some symplectic Grassmannian set?
We independently, so what is very curious is that even at 4 points, just using the lambda and the lambda tildes, we can saturate the C matrix. And the C matrix satisfies all the symplectic Grassmannian conditions, which we know. And the minors, little group invariant minors, little group is a global symmetry in this, and little group invariant minors correspond to Mandelstam's, which we know. But we have one less Mandelstam than what is required for GL1 invariance. So this is the issue. But we think that perhaps this Jacobian is related to this GL1 somehow, because now we have to merge objects that amalgamate to produce also this Jacobian factor. So this is just a vague idea we have, but the GL1 issue remains. Even at 3-point, if we just understand the geometry of the 3-point amplitude, then and add all the extra conditions for C, we see that there is no GL1 invariance again at 3-point. So we have to add something extra such that it glues nicely, and the extra things should produce this Jacobian factor in the end. So this is the idea we have so far. But yeah. Let's see. Thanks.
Any other questions? If not, let's thank Subramanya again. And maybe one last round of applause for all our speakers.